Inshallah, inshallah. Yeah. Yeah. So this is the part that we did in the last class, right? And yeah, let us do one question and then we'll start the new chapters. Now, everything will take only few classes. So atoms and nuclei, they will take only the chapter, right? Magnetism and matter, so I will start that one. Okay, and then we'll start the revision again. So we'll do a couple of questions and then all those revisions. Okay, so the question is like this, right? And the question is related to photoelectric effect and all the graphs you guys remember, right? All the graphs you guys remember. So first graph was yeah. So first graph was why this is the so what was the first graph that we understood? First graph was this, right? This was photo current. This was intensity, right? This thing we understood. And then we understood about this thing. So this was, right? So this was potential at collector and this was stopping potential and this was saturation current, right? And all these where so all these have different intensity, right? So I3, I2, I1 intensities. So this graph told us that how different intensities will have different saturation current and but same stopping potential, right? And from this graph also we learned that the stopping potential has the maximum kinetic energy of that electron, right? So this we understood. And yeah, so this was the first thing that we understood, dependency of intensity, dependency of saturation current. And then we also learned about this graph, right? So this graph was like this, right? So what were these variation? Do you guys remember that? So these were different what? Do you guys remember? Guys remember or you guys have forgotten? This was again photocurrent. Yeah, this was photocurrent and this was potential, right? But
Yes,
what were these three different lines? These were different frequencies, right?
frequencies.
So this was mu3, this was mu2, this was mu1. So we understood that the stopping potential depends upon these different frequencies, right? And then the
Yes, sir.
last graph that we understood was this was frequency. This was the graph that we understood, right?
And
This
stopping
was
potential.
Yeah, this was stopping potential, and this stopping potential is also related to uh, also related to kinetic energy. So this we can also write. Right. Now the question that I'm going to ask is one, right. So the question that I'm going to ask is from the graph. Right. So we have this graph. Let's say this is 0.5 into 10 to the power 6 hertz. Let's say this is 3.8 into 10 to the power 6 hertz. And this is frequency and this is potential, stopping potential. Or I can write kinetic energy, right? So now can you guys tell me that there are two questions from this thing. One is that what would be the threshold frequency? What is threshold frequency from this graph? And the second thing is what is the work function? These two things you guys have to calculate. So first part, what would be threshold frequency, guys? Can you guys tell me? What is threshold frequency from this graph? Yes. What is threshold frequency? Yeah. Guys,
2.5 into 6.
so Mariam is saying 0.5 into 10 to the power 6. What are your answer, guys? Are you guys agreeing to this answer? Yes. Aisha, Arsalan, Mir. What do you guys say? Yeah. What do you guys see? So don't you guys remember that in this graph, right? In this graph told us that it require a minimum certain frequency so that this surface ejects the electron, right? Otherwise, the stopping potential or kinetic energy would be zero, right? If we
Yes, sir.
don't if we don't reach this thing, then the stopping kinetic energy that would be zero. And as soon as we reach this frequency, which is the threshold frequency, then the surface will eject the electron, right? So this is the minimum required frequency. This frequency we have to overcome. So what do we remember? Kinetic energy was h nu minus uh, phi naught, which was h nu naught, right? So this was the thing that we understood from the photoelectric effect by Einstein. So this is the threshold frequency, right? Mariam is correct. Yeah. Now what would be the work function? Work function phi naught was related with this threshold frequency, and that was what? H nu naught. So this would be how much? That would be H is Planck's constant, right? And this Planck's constant value is how much? That is 6.626 into 10 to the power minus 34. And what is the unit? So unit would be, let's say, we know that E is H nu, right? So E is joules and nu is per second. So this second goes here, so this is joule second, right? So this is 6.626 into 10 to the power minus 34 into zero point 0.5 into 10 to the power 6. This would be how much? Whatever this answer is, it's a calculator. 6.626 into 0.5. So that is 16.565 into 10 to the power minus 34 and 6, so minus 20. And then we can also write this as 1.656 into 10 to the power minus 28. So that would be not minus 28, but minus 27 joules. Right, and if we remember, we write we write all the energies in this chapter. In what units we write all the energies? Do you guys remember what is the unit in this chapter of energy? That is the first thing that we did.
Joule.
Yes, no,
Joule.
Julie, you can see that if we write it in joules, so that is very small value, right? Then we converted this joule into some another quantity. That was electron volt, right? So in particle physics or in structure of atom or all these scenarios, whenever we are writing the particle nature of radiation, so we write the energies in electron volts because this is a small unit, right? As I was giving in previous class, I was telling you guys that we require some inchy tape to measure the general physical bodies that we see, right? So we require a suitable measurement. So that is why in these chapters we will use electron volts. So how much is one electron volt? You guys remember? How much is one electron volt? Yes. How much is one electron? So remember, one electron is 1.6 into 10 to the power minus 19. Right, volt is 1 volt, so that is in SI unit, so that would be joules. This is the conversion, right? Always remember this. And if we want to write joules in electron volt, so we have to do what? We have to divide this thing. So 1.65, let's say 6 into 10 to the power minus 21 divided by 1.6 into 10 to the power minus 19, and that would be electron volts. So this would be how much? This is 1.66 divided by 1.6. That is 1.03. And 10 to the power minus 27, and this minus 19 goes upstairs. So this would be 90 electron volts. This would be 1.03 into 10 to the power minus 8 electron. Now this is sufficient, right? So this is looking promisable, right? Because this minus 27 is pretty small value. If if you think this minus 27, if you think about this, so this is 0.00000, you reach $27. So this is very small value. So we should write all the energies, particularly in this chapter and in nuclear physics, we write all the energies in electrons. So this would be the work function. This much energy we provide to this thing, to this material, so that it can eject one electron. So that is the idea. Is this thing clear, guys? Is this
Yes,
thing
sir.
clear? Okay, and remember, if you have heard already about in chemistry classes, so what is the energy that you write in structure of atom of hydrogen atom? Do you guys remember? You write it as minus 13.6 by n squared, right? So you write the energy in electron volts. So that is why this unit is very important, right? I don't, yeah, if so, we'll see about this energy in course order, but yeah, for now, okay, you guys quickly note it down, and then we'll start the next chapter. Quickly note it down.
Done, sir.
Done already. Okay. What about all of you guys? Noted?
Yes, sir, done.
Done. Okay. So now let us next chapter, which is oh, and the first thing that we understand is the chapter, right? So the first thing that we should learn or understand that what scientist, who was the person started this idea of atom, right? Who was the first scientist? So do you guys
Bohr.
remember? Yes? Ye- Yeah. What are you saying, Maria?
Bohr.
Bohr. So Bohr was, yeah, among the latest guy, right? Was the last guy who started, who initiated this idea, atom, right? Atomic structure started. Because we have to remember everybody's contribution, right? Let's say you are given a project and all the credits, let's say someone take all the credits and rest of the person, they don't get any credit, right? That should be wrong. That should be unjustified. Yes, Aisha. So the idea started from, so the first scientist that gave the idea was Dalton, right? John Dalton started the idea of atom, and he was, so his achievement was, what was his achievement? So he gave the idea of atom, right? He told that every matter, he told that every matter is made up of something very smaller, fundamental thing, right? And that fundamental thing he gave the name atom. So he gave the idea of atom. But what was his drawback? This you have already learned in your 10th standard. I'm just recapping that. So what was his drawback? Yeah. What was his drawback? Do you guys remember? Yes. So drawback was that he told that atom is the fundamental unit, and it cannot be divided into further smaller units. Right, and now you guys have already know the structure of atom, right? So you guys can clearly say that this is wrong, right? Fundamental. So he said that the smallest unit of a matter is atom, is an atom, right? We cannot divide atom any further. So this was his drawback. So then came the other scientist, and he was J.J. Thomson, right? So he gave the idea of, so he told us. that atom is made up of protons and electrons, right? Until that time, the nucleus was not right. Nucleus was not discovered. Neutron was not discovered, right? So you say that atoms are made up of protons and electrons, and he also. So this was his idea, but his drawback was right. So his drawback was that it cannot explain the emission and absorption spectrum of elements. Right. So this was his drawback, and then came the right. So then came Rutherford, and he said that gave the idea of nucleus and electrons revolve around it in circular orbits. So this was the idea that he right achievement. This was his achievement, but the drawback was that it cannot explain the. We will understand it further, right? It cannot explain the fine line in element spectrum, right? So these were certain few of the scientists who developed the idea of atom, and these were some achievements and some drawbacks of all of them, right? So you guys please note it down, and then we'll extensively talk about this rather, right? So this cake model, what was this called? Watermelon model. This you guys have already learned in your 10th standard. So we will extensively talk about this Rutherford, right? So you guys please note it down. And then we'll talk about the Rutherford.
Done, sir.
Done, sir.
Okay, everyone noted? Yeah, Aisha and me, what about you guys? If you guys have noted, then let's talk about Ernst. Oh, So Ernst Rutherford gave the idea of the structure of atom. So his research scholars, right? His research scholars H. Giger and E. Marsden made the experimental setup, right? This was the first thing. They made the experimental setup. These two scholars, which were working under Rutherford, they made this experimental setup, and they used. So, what is the thing that they used? They used alpha particles, right? What is an alpha particle? An alpha particle is helium nuclei, right? What would be a helium nuclei? So let's say in your 10th standard, you guys have already learned that what is the helium nuclei? What is the helium nuclei? Okay, what is the helium atom? This thing and you guys have learned in 10th standard. This text. What is the helium nucleus? What is the helium nuclei, guys? So helium atom. So from
Two
the
electrons.
yeah, so you have this nucleus, you have this N plus P, right? And you have two electrons. This is the helium atom, right? This is the helium atom. And what would be helium nuclei? So if you remove these two electrons by some providing some energies and whatever you do, you remove these electrons from this thing. Then what you will have? You will have only this nucleus and two positive charges, right? So this alpha particle is helium plus ion, which is the helium nuclei, right? Is this clear, guys? So this is called the alpha particle. It is a heavy particle, right? And it has some high energies. So Ernst used this alpha particle in his experiment because this is a heavy particle and it has a larger energies, right?
Yes, sir.
So then he used this thing, right, alpha particle. And what was the experimental setup? So let's say there was this. Yeah, you guys can look into the NCRT book, but I will make the rough sketch. So you have this alpha particle, right? You have this source. This source is emitting alpha particle, right? So this source is emitting alpha particle in every direction. But you make this lead collimator, right? So what is the purpose of this lead collimator? So they create a beam of alpha particle in one direction, right? Because all the alpha particle are going here and there, but through this collimator, so they provide the direction of this alpha particle, right? And then these alpha particles strike on this gold foil, right? So they strike this gold foil. And let's say if you have some tennis ball, right? And if you strike on that big ball, so what happens? If you have some matter, and you strike on some wall, then what happens? It will bounce back, right?
Yes, sir.
It will bounce back. So this is a gold foil, right? This is a gold foil. This is a surface, and you're striking something with it. So it should be bouncing back, right? This should be the initial idea, right? Right, guys?
Yes, sir.
Yeah, but it didn't happen. They observed a totally different scenario, right? They observed a totally different scenario. And what did they do? Have this gold foil. Why did they use this gold foil? Right? Because this gold foil was very ductile, right? We can make a very thin sheet of this gold foil, right? So let's say you have this gold, right? You have this. Let's say you zoom this gold plate. So this would be the gold plate, right? This would be the gold plate. I'm not making all the central atom and all these valence shell and all these. So this would be gold plate, right? But if you make, but let's say it is metal is very ductile, and then you can make a very thin sheet. So only this sheet that you have, right? So if we make a very thin sheet, so then it will on the surface it will have only few amounts of layers, right? So there would be large layers if this is thick, right? But if you make a very thin layer, so you will only have less atoms on one surface, right? The surfaces would be very less. So that's why you used, that's why not we, but Rutherford used this gold foil, and the thickness of this gold foil was, you cannot imagine that how did they make this thickness, but this was 2.1 into 10 to the power minus 7 meters. Can you guys imagine this? How thin is this? Right? This is nearly the size of the atom, right? So we have made let's say an atom out of this foil, right? So that is why they used this gold foil. They made a very thin sheet, and they predicted that all the alpha particles will bounce back. But they didn't see this kind of situation. And then you had then you have this screen, right? And this was this was photosensitive, and some sensitive screen was there. And by glowing this screen, they can observe what part is getting striked and what part is not getting striked, right? So all these things they observed in this screen. So this was their setup, right? They use this alpha particle, and they use this collimeter, and then they use this input point. So what did they observe, right? What did they observe? The first thing that they observed was to most of alpha particles went forward without any deviation. So most of the alpha particle passed through this copper without any deviation, right? And few of the alpha particles passed through the few of the alpha particle passed through the foil, with little deviation or small deviation. And the third one was that very few of the alpha particles passed was with larger. And then the last thing that they observed that one out of 8,000 particle, alpha particle, came back from the world. Right. So, what was the observation they made? That let's say this is your atom.
Sir,
Yes.
so your voice is really low.
Yeah, my voice is very low. Okay, one more. Give me one. Why didn't you tell me sooner?
He was fine earlier, but now it got low.
Oh, okay, yeah. Why this happens sometimes? Maximum. Let me again. Yes. Can you guys let me know how is it now?
Sir, we can hear you, but like your voice is like really
Very
low.
faint.
Like
Very faint. Yeah.
yes,
So
few
as if
words are not audible.
okay, as if I'm speaking from a very far away distance, right?
No, not like that. It's like as if um like my application's sound is like very low, but it's not low. Like it's on maximum.
Okay, yeah. So what I have, yeah, what I have, I can disconnect it and yes, sir. How is it now, guys? Can you hear me properly? How is it now?
Yes, sir. It's nice.
Good, good. Okay, so now I'm audible. So what did they observe? What did they observe that most of the alpha particle went past through it, right? Some of very few of them, right? Very few of them with a small deflection, right? This is the deviation angle, and very few. So if this is crucial, right? Very few of them with larger deviation, right? So this has a larger deviation, and only let's say one in 8,000 came back. This went there and it came back. So these are the observation that they made, right? So what can we tell about from this these observation that we can say that most of the space in atom is empty. Right. Second, we can say that electrons. So there is a positive charge situated at the center where all the masses are there, right? Which constitutes of all the masses. And thirdly, the electrons revolve around that nucleus in a circular orbit. These were the conclusion that they made, right? So all the mass is centered around this part, right? There's a positive charge in there that is called nucleus, and the electrons are revolving around it, right? So these are the final conclusion that Rutherford made, right? So you guys please note down this part, and then we'll write down the other aspects of this, right? Please without yeah, whenever you guys want me to scroll down, please.
So can you please scroll down?
At the center, I should write called nucleus.
Yes, certain.
Done. Done, everyone. Noted.
Just a second, sir. Yes, sir. Done.
Yeah. Okay. So now let us understand a few important things about this. About this Rutherford model of it, right? Why? The next thing is trajectory of alpha particle, right? So we can write, yeah, we already know that we have this atom, right? And there is this certain positive thing which is there, right? And the alpha particles are, right? Right. So these are different trajectories. And what we can write from here, right? What we can write or understand that we can represent this thing through a graph, right? So through a graph we can represent this thing, and how can we represent it? So if let's say this is the deflection angle, right? And this is the number of alpha particles. So we know that at smaller angles, right? At smaller angles, the deflection would be very small, and as we increase the deflection angle, so there will be less amount of alpha particle, right? So for a larger angle, right, you can see from here that for larger angles there would be very few deflections, right? For a larger angle there would be very few alpha particles, and most of the alpha particles will have zero deflection, right? So most of the alpha particles will have zero deflection, and then this will go decrease gradually, right? So this would be the graph of the trajectory. So is this clear, guys? Is
Yes,
this
sir.
okay? So you guys please note it down, and then we will understand about. Yeah, then you write.
Done.
Okay. So what about you, Arsalan, Aisha, and me? What about you guys? Noted.
Yes, sir. Done.
Yeah. Right. So the next thing is distance of closest approach. Right. So what is the distance of closest approach? So we know that the alpha particle is moving, right? So if we consider this diagram, right? So let's say the alpha particle is coming straight at this right. So it is coming straight at this nucleus, right? So the alpha particle is coming straight. This alpha particle, so this is positive, right? This alpha particle, what is the charge of this alpha particle? What is the charge of this alpha particle?
Negative. Positive.
Positive. That is helium 2 plus, right? Right. This is helium 2 plus. So this is positive. So you have alpha particle which is positively charged, and it is coming at this positive charge gold foil, right? So if it is coming straight at this thing, so there is what kind of force would be acting on this thing? Let's say this is positive charge. Positive charge is coming, right? So what will be the force that will be acting on this thing?
Attractive force.
Attractive. This is positive. This is positive.
Oh, repulsive. Repulsive.
Repulsive, right? So there would be a repulsive force from here that is acting, from here that is acting, from here that is acting, from there it is acting, right? So repulsive force, I will write the things in there. So that would be proportional to 1 over r square, right? You guys already know from your electrostats, right? So this is the force, repulsive force, which is acting on this thing, right? On this alpha particle. And this alpha particle is coming with some kinetic energy, right? So due to this repulsion, there is this potential energy. And when this kinetic energy, because it is coming with some kinetic energy and it is decreasing due to this repulsion. Because at this point, force of repulsion is less. When it reaches here, the force of repulsion increasing, and when it reaches here, the force of repulsion overcomes the kinetic energy, right? Then then this alpha particle will stop and it will be pushed back through this repulsion, right? So the closest that this alpha particle can approach is called the distance of closest approach, right? So at distance of closest approach, right? At distance of closest approach, the kinetic energy of alpha particle becomes zero, right? And second thing is that all the kinetic energy is stored in the form of potential energy. Right. So at this point, let's say this is some r distance, right? R naught distance. So at this r naught distance, every kinetic energy, right? All of the kinetic energy has become the potential energy. So let's say it started with v velocity, right? It started with v velocity. So the kinetic energy becomes the potential energy at here, right? So law of conservation of energy. Now, you guys can tell me that you guys have already learned this electric charges and fields, and you guys know that what is the potential energy between two charges. If you have this Q1 thing, if you have this Q2 thing, and if you have this separation R, so can you guys tell me what is the potential energy? Yes, what is the potential energy, guys? Do you guys remember? Yeah, what was the potential energy, guys?
KQ1 Q2 by
Yeah,
R.
absolutely right. So this is the potential energy, right? So this potential energy would be in here. So we know that this kinetic energy of alpha particle, potential energy of this atom, right? Or this nucleus. So kinetic energy of alpha particle is half mv square, and potential energy would be how much? So that would be k. What is the charge of alpha particle? What is the
Positive.
charge? Yeah, so how many electrons you have lost? How many electrons you have lost in helium plus
2.
net 2, right? So the charge would be 2 plus 2, right? This is the charge of alpha particle. And let's say the atomic number of this thing, atomic number of this whatever gold foil or whatever metal or whatever element is Z, and there are electrons, right? So there would be Ze electrons in this thing, right? So there would be Ze charge on this atom, right? On this nucleus. So this is this thing and divided by this R naught square R naught, right? So that would be the potential energy. So if we write this thing, so that would be how much? That would be half mv square and k or z e square, right? Divided by R naught. So if we calculate this R naught, that would be how much? That would be 1 by 4 pi epsilon naught and 2z e square divided by half mv square. So that would be the distance of closest approach. Distance of closest approach. Right. And yeah, this is experimentally, it is found that it is equal to the size of the nucleus, right? So it is equal to the size of nucleus that we will learn later. If this part is here. But in the next section, in Bohr's model, you see that this is in the order of the size of the nucleus, right? So you guys, please note it down, and if you guys have any doubt, please tell me. Okay, please note it down.
Done, sir.
Yeah, and all of you guys have noted.
Yes, sir.
Done, everyone. Yes, Aisha and me. What about you guys? Yes, what about you guys? Noted. Yeah. Okay, so now let us understand about next thing, and that is the parameter, right? This is the parameter. And what is this distance, right? So let's say you have this center line of this new, if this atom, right? So let's say you have this atom, right? And this is the center line of atom. And this is right, and this is the path that the alpha particle is following, right? So it will strike at this part, right? And it will make an angle of deviation from here. So this perpendicular distance from the velocity vector and the center line, right? So this is the velocity vector of alpha particle, and this is the center line, right? So this distance is called this B parameter, right? So this is the B parameter, and it governs the deflection angle, right? So let's say, yeah, the derivation is not there, but I will write only the result. So this B parameter is related as 4 pi epsilon naught and Z E square cot theta by 2 and half mv square. So this is how this B parameter is related, right? So what is this B parameter? B parameter is the distance, or I should write the perpendicular distance between the center line of atom and the velocity vector of alpha particle. And now you guys can tell me that if this b distance, if this b distance is small, so what will happen to the deflection angle? Will it be smaller or will it be larger?
Larger.
Larger, right? And you guys can see from this thing also, right? So if you have this b smaller, then cot theta by 2, that would be smaller, right? And for what value cot theta is smaller? So how this cot theta changes, right?
Sir,
Yes,
if B is larger, cot theta by 2 will be larger, right? Because
yeah,
it's
yeah,
in the
yeah, yeah.
middle.
So yes, absolutely. Right. So if b is larger, this cot theta would be larger. And I wanted to tell that I say that if b is smaller, right? So if b is smaller, then cot theta, yeah, that would be smaller. And yeah, absolutely right. So if how this cot theta varies, if you guys remember how this cot theta varies, so we remember that tan theta goes from let's say 0 to 90. So how this varies? It varies from 0 at 45 it becomes 1, and at 90 it becomes infinity, right? So we know that the variation of tan theta, it goes like this, right, guys? This is the
Yes,
variation of tan theta. So at 0 degree, it is 0, and then it increases. But what about this cot theta? Cot theta is totally opposite, right? So it is maximum for 0 degree, and then it becomes 1, and then it becomes 0, right? So this is how the cot angle varies. So if I have cot theta value higher, then what is this theta angle? Did you guys understand this part? So if the key parameter is larger than the deflection or deviation, then cot theta by 2 would be larger. And correspondingly, the deviation angle theta would be what? If this cot value, for what kind of angles, what kind of angle cot value is larger?
0.
0, right? So for small angles, this cot value, so if I make the graph of this cot theta, the graph of cot theta is what? This is going from infinity to 0. So this is the graph of cot theta, right? So at pi by 2, it becomes 0. And if you reach the smaller angles, so at smaller angle, it is becoming higher and higher. So this is the graph of cot theta, right? So the angles are small, if the angles are small, then value of cot theta that is larger. So if cot theta is larger, then the deviation angle would be small.
Smaller.
Yeah. So, yes, you are correct. Similarly, we can write the opposite thing that if the p parameter is smaller, right? If this distance, and we have already seen this from experiment, right? We have already seen that if this if this b distance is larger, then it will just pass on this nucleus, right? This atom. So there will be no deflection. And if there is no deflection, then this deflection angle is small. So that we already know from the observation, right? Where are those things? Yeah. So in here we see that this is the central line, right? This is the central line, and if we increase this b distance, then the deflection angle are getting smaller and smaller. And if we increase this if we decrease this b distance, let's say if this is the b, then the deflection angles are increased, right? So that is what this b parameter tells. So if the b parameter is smaller, then the cot theta by 2 value would be smaller. Subsequently, the deviation angle theta would be larger. So these are the things that we get to know from. Yeah, these are the things that we get to know from this Rutherford model. You guys please note it down. And if you guys have any question, please tell me, right? Please note it down. What is this B parameter? Yeah, so this is called impact parameter. Right? This is impact parameter. This B parameter is called impact parameter. So how much impact or collision? So this is also the collision parameter, right? So if the P parameter is small, so there would be a larger impact, right? This P parameter is called impact parameter. You guys please note it down, and then yeah, we'll write the drawbacks of Rutherford model.
Sir, can you please scroll down a little?
This is the impact.
Sir, the last 2 points also we have to write.
Yeah. So these are important, right? What is the dependency of this P parameter with this deviation angle, right? So this theta is the deviation angle. This is the impact parameter. What is the relation, right? What would be the variation if we changes this b value? So that part we have to write. Yeah, whenever you guys have noted, please tell. Mariam has noted. What about rest of you guys noted? Yes, guys. What about you? Done, guys. Okay, so now let us write the drawback of and then this topic would be over, right? So first thing is that, right? So let me just skip all the things. What are the things that we have learned? So first we have learned about the distance of closest approach. Then we have learned about this impact parameter, right? And then we have learned about the structure. So these are the important things that we have learned from the Rutherford model, right? Remember that why did we use this alpha particle? Why did we use this gold foil? And all the other things that we have talked about, right? Now, right, if this was successful, then why did we discarded this model, right? Because if this is correct everywhere, so what is the need to discard this model, right? But there were some problems. The first problem was the stability of it, right? Stability of it.
Sir,
Yes. Again, my voice is weak.
sir, yes, sir.
Why this is why this? Because I have not done anything right, and I am speaking with the same frequency and amplitude, right? Yes. How is it now, guys? Is it okay?
Yes, sir.
Okay. Yeah. So I didn't do anything at all. I just the plug and then and then replugged it. So I don't know what is changing. Why? So stability of atom, right? This was the first drawback, and the second was the continuity of the spectrum, right? So these were the main two problems of the Rutherford model. We'll talk about them in detail, right? One tells us that if we move in circular orbit, right? So then there would be some acceleration. And if there is some acceleration, if you have a charge particle, right, electron which is accelerating, then it will create some electromagnetic wave, right? And we already know that those electromagnetic waves have some energy. So this is rotating and this is making an electromagnetic wave. It is generating electromagnetic waves. Then there would be some energy which is being lost in the generation of that electromagnetic waves. Then this circular orbit would be smaller, right? Because the some amount of energy has been lost in electromagnetic energy, and again the energy is being lost, and again the energy is being lost, and ultimately the electron will fall on the nucleus. That's right. So yeah, we'll stop at here, right? Oh, my video is not on. So we will stop at here and see you guys in the next class. Okay. So we'll talk about this thing and then we'll talk about Bohr's model and then this chapter is over. Guys, they're very right. These chapters are pretty small. It will not take that much of a time, and